Hello everyone, my name is Walaa Asakly and I am from Browdy College in Israel. Thank you for watching my video. Today I will talk about the sum of elements preceding records in set partitions. We start with short motivation. My research focuses on statistics in combinatorial structures. Today, the combinatorial structure we consider is set partitions, which are among the classical objects in combinatorics and have been studied for many years. Recently, researchers have shown interest in record statistics. This naturally led me to investigate the sum of elements preceding records in set partition. Okay. The first work that inspired me was a paper by Mansour, Koppenmacher, and Wonger on records in set partitions. They studied records and several related statistics. This motivated me to study the sum of weighted records in set partitions, and later published a paper on this topic. After that, I started thinking about another question. Instead of counting records themselves, what can we say about the sum of the elements that appear before records? Before presenting the results, let me introduce the main definitions that we will need. The first definition is set partitions. So, a partition pi of set N of size K, and also called a partition of N. Here the set N contains the elements 1, 2 to N with exactly K blocks, is a collection B1 to BK of non-empty disjoint subsets of the set N, and their union is equal to the set N. These elements BI are called blocks, and we have an order in these blocks. These blocks are listed in increasing order of their minimal elements. That means that minimum of B1 is smaller than minimum of B2 and smaller than minimum of BK. Let me show you an example. The partitions of the set 3 with exactly K blocks are, we have here 3 options. The first option is the subset of 1 and the subset of 2 and 3. The second option is the subset of 1, 2 and the subset of 3. And the last option is the subset of 1, 3 and the subset of 2. Here we have a notation and properties of the set partitions. Okay, so the set of all the partitions of N, of the set N, with exactly K blocks is denoted by P in K. And the size of this set is equal to S in K, which is Stirling numbers of the second kind. And without fix the number of blocks, that means that the set of all partitions of the set N is denoted by Pn. And the size of this set is equal to Bn, which is the nth Bell number. Okay. Here we have another representation of any partition. So any partition pi can be written as pi1, pi2 to pi n, where I in b pi I for all I. And this form is called the canonical sequential form. That means, in particular, every set partition of the set N with exactly k blocks can be presented by a word of length n over the alphabet k. And this correspondence is 1-to-1. Let me show you an example. Here we have a partition of the set 4 with exactly 3 blocks. So we have the subset 1, 3, the subset 2, and the subset 4. Okay, so the corresponding word is a 1, 2, 1, 3, because 1 in block number 1, so the first letter is 1. 2 in block number 2, so the second letter in the word is 2. 3 in block number 1, so the third one is 1. And 4 in block number 3, so the fourth one is 3. Okay, the next definition, a record or left to right maximum. So we consider the canonical sequential form of a partition pi, and we say that pi I, this element pi I, is a record of position I if pi I greater than pi j for all j from 1 to I minus 1. Okay, that means that the element pi I, the record, is greater than all the elements before it. Here we have an example. We have the partition of the set 4 with exactly 3 blocks, and the corresponding canonical sequential form is 1, 2, 1, 3. And we can see that all the elements in red are records. First of all, 1 is the first element, so it's greater than all the elements before it. 2 also, the second record of position 2, and it's greater than the element before it. 1 in black is not a record because it has elements bigger than it before it, and 3 is a record of position 4. Okay. Now I want to define my statistics. Okay. So the first statistic is sum. What is the sum? Firstly, we need to define sum A, where sum A pi, where pi is the corresponding canonical sequential form of a partition pi to be the sum of all elements preceding a record in pi. And we define sum pi as the total sum of all such sum A pi over all records in pi. So here we fix any record, and we need to find the sum of all elements before it, and here we don't need to fix it. We need to find for all records in pi. Here we have an example. we have a partition of the set 6 with exactly 3 blocks, and this is the canonical sequential form of this partition. So we can see that the sum 2, 2 here, and it is a record. Only the element that this is a sorry, it's a record, and the sum of elements before it only 1. 3 here in red also a record, so the sum of the elements before it is 1, 2, 1, and 1, and the sum pi is equal to sum 2 and sum 3. Okay, so the ordinary generating function for the number of set partitions according to the statistic sum. So before we need the formula for pKAXQ, which is the generating function for the number of set partitions of n with exactly k blocks according to the statistic sum A. So pKXQ is the generating function for the number of set partitions of the set n with exactly k blocks according to the statistic sum. So the variable q counts the sum pi. Okay. Let me now show you some results about this research. So here we have a formula for the generating function for the number of set partitions of the set n with exactly k blocks according to the statistic sum A. And this is the formula. And of course, if we want to find the generating function pKXQ, we need to sum over all k from 1 to n. So we will get the following result. And this is the form for pKXQ. Okay, so main results. The total number of sum over all set partitions of n with exactly k blocks is this number, and we can see that this number we can express by the Stirling numbers of the second terms of the Stirling numbers of the second kind. So it's really a nice result. I would also like to mention that only recently we find a combinatorial proof of this formula. So what is the main idea of the main idea of the proof? By using a generating function, we take the corresponding generating function and we differentiate it with respect to the variable q, which counts the statistic, and then we substitute q is equal to 1, and the last step is we need to find the coefficients of x power n in the expression. Okay. Note that a natural way to obtain the total number of sum of elements over all set partitions of n is to sum this term over all possible values of k. However, we were not able to obtain a nice formula in this way. So instead, we use the ordinary generating function that we have already derived, and converted it into the corresponding exponential generating function. And we differentiate the exponential generating function and substitute q is equal to 1, and we find the coefficients of x power n divided to n factorial, and we have this formula. Okay, so the total number of sum taken over all set partitions of n is given by, note that this is very nice expression because it's in terms of Bell numbers, so it's nice. Okay, the last result that I want to show you today, asymptotically, as n goes to infinity, the total number of sum taken over all set partitions of the set n is given by this expression. That's it, and thanks for attention.